We'll start with number 14. Right on 14. The directions say to find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. So our equations are y equals 6 minus 2x minus x squared and y equals x plus 6. So for part A, we're supposed to take this about the x-axis. All right, so you know the preliminaries. You write down what your axis of revolution is, so about the x-axis. Draw your graphs. So the one there on the top is the y equals 6 minus 2x minus x squared. The one on the bottom is the line y equals x plus 6. And all I'm concerned with is the region that's bounded by those graphs. So I didn't draw the whole graph. I mean, I originally did on my calculator, right? But on my paper, all I put was the part that made the region that was going to be revolved. To me, at least, it's a little simpler if I don't have to put more stuff on there. All right? So that region is going to get revolved about the x-axis. So you draw in a rectangle that's perpendicular to your axis of revolution. And when you do, you see that the width of that rectangle, which is the height of the disk or washer, is dx, which tells us everything's going to be in terms of x, which is good news considering when you look at y equals 6 minus 2x minus x squared, I would not be looking forward to trying to solve that for x and turn it into a function of y. Okay? So that's actually good news. What I don't know are the boundaries. So I need to know, so everything's in terms of x. So I need to know the x-coordinate right there and the x-coordinate right there, because those will be my limits of integration. So to find those points of intersection, or more specifically, to find the x-coordinates of those points of intersection, set your graphs equal to each other, set your functions equal to each other. So you do that. It takes you a couple steps of algebra. And we find out that 0 and negative 3 are those x-coordinates. Okay, so at this point, we know that much about our integral, okay? Because it's pi r squared h for the volume of a cylinder. So pi's in front, the h, the dx is in the back. Now everything that I just marked out in red, that's what we got to worry about. So we need to decide when we revolve this rectangle about the x-axis, do we get a cylinder or a disc, or do we get a washer? We get a washer because there's a hole in the middle, isn't there? Okay? So I wrote down washer because that helps me understand, or helps me keep in mind, I've got to have an outer radius squared minus an inner radius squared. Okay? The outer radius starts at the axis of revolution and it goes to the outer function, the outer edge of the rectangle. So the outer radius starts here, goes all the way to here. So what's that distance? Well, it's whatever the y-coordinate is, right? But I can't put y, so instead I put 6 minus 2x minus x squared, okay? If I could put y, that'd be awesome, right? But I can't, because everything's got to be in terms of x. So the length of that outer radius is 6 minus 2x minus x squared. And don't forget, it's outer radius squared. So then I got to square that trinomial. Minus. Question? Minus. Now, the inner radius. So let me erase that blue line and make a new one. The inner radius goes from the axis of revolution to the inner function, the inner edge of the rectangle? Well, again, it's whatever that y-coordinate is. It's a different y-coordinate this time, though, isn't it? So instead of putting 6 minus 2x minus x squared to represent the y-coordinate, I put x plus 6 to represent the y-coordinate. And then it's got to be squared. Inner radius squared. All right, so you with me to here? Okay. Then you do a tremendous amount of number crunching. And after you do that tremendous amount of number crunching, it's not so bad. We get down to here. Now we do antiderivatives, and then we do substitution, and you see where that takes you. All right, besides just writing down the stuff, any other questions on part A? All right, well, you can go back and get this off the video then. Let's go to part B, because part B is pretty challenging, I think. Okay, so let's look at part B. I've got the same figure, so I've at least knocked out some of the preliminary work, right? I know what the limits of integration are. I know what the figure looks like. It's about the line y equals 3. That's horizontal, so the rectangle's the same place. It's a dx. So having done part A, I get that much of part B done very quickly. Okay? And that's not always the case, right? Sometimes they give you that second one where they've shifted to a vertical axis and you got to refigure out the limits of integration and all that. But they didn't. So we'll take advantage of that. All right. The tough part here is figuring out the radius is. Oh, radii. There's a word for that. Radii. Yeah. Phew. It'd be radius in anyway. You done seen it? All right. Where was I? Oh, outer radius. All right. The outer radius starts, by the way, washer, because of this little space right there between the axis and the figure. Okay? So the outer radius starts at the axis and goes to the outer edge. So it's just that. It's not as long as the outer radius was in part A because the axis of revolution moved closer to the region. Okay, the region didn't move, but the axis did. It got 3 spaces closer. Doesn't that mean the radius is 3 shorter? Yep, it's the function minus 3. I don't think I've ever explained it that way before, but that makes sense to me. Since the axis moved closer to the region, the radius got shorter. So, how much shorter did it get? 3 spaces shorter. You know, if you had it on grid paper, you'd count 3 spaces. So how do you account for 3 spaces shorter? By subtracting 3 from it. Okay? Is the same thing going to happen on the inner radius? The exact same thing is going to happen on the inner radius. The inner radius will be 3 spaces shorter than it was in part A. So take that x plus 6, subtract 3 from it. Now I'm going to pause here for a minute. But get that written down. Yes, we need to simplify inside the parentheses before we square. Now this was a rare thing for our book. in that part A made part B a little easier. And that really, it doesn't usually work that way, does it? Okay? So what if we hadn't done part A? How would we know to do that -3 at the end of each radius? So let's pretend part A was never done. How would we know? Well, we would know like this. If you're measuring a segment with a ruler, but your ruler's broken and there's no 0 on it, okay? So you can't start measuring at 0. But you line one edge of the segment up at 6 inches, and then the other edge of the segment is at, let's say, 4 inches. How do you know how long that thing is? 6 minus 4, right? It's 2. Same idea. We're needing to measure that blue segment, but we're not starting at 0, because 0's down here. That's where the 0 is. It's broken off. It's not there anymore. Pretending, okay? So how long is that blue segment? It's whatever that measurement is minus whatever that measurement is. Correct? What is the top measurement there? The function. What is the bottom measurement there? 3, because they told us the axis of revolution is the line y equals 3. So the top minus the bottom gives us the length of that blue segment. Does that make sense? So that's how I know it's the function minus 3. Okay? Are with me? I'm not sure I've ever explained it just like that before either. That makes sense to me too. What am I, some sort of genius? At which point in my house somebody goes, yeah, some sort. You were thinking it? Yeah. It's usually me that says that. I'll call one of my kids, you know, they'll fall down the stairs or something. What are you, some sort of genius? Yeah, well, see, that would be called sarcasm. Okay, when you do something stupid, and kind of like Brian Regan. You know, Einstein's supposed to be one of the smartest guys ever, but yet his name is an insult because you do something really stupid. Way to go, Einstein. You know. All right. Then do the same thing for the inner radius. It's this little blue segment right there. What's its length? Well, it's that measurement minus that measurement. So it's the function x plus 6 minus the measure of that bottom y coordinate, which is 3. So really, it's always that, isn't it? Not y squared. Genius. It's always that, isn't it? Every time. To get the radius. Back in part A, it was y2 minus 0, but that's still that distance for the outer radius, isn't it? Okay? Does that help a little bit? And then, in theory, once you get that figured out, you can work the rest of it. There's a lot of places to make a mistake. There really are. But you crunch your way through it. So, again, I'll let you go back to the video to get the rest of that written down. You can hit pause, then it stays just like that. Let you write it down, then you can hit play, and it keeps on going. You already knew that, didn't you? All right, one more. '62, which part? 62, the one with the circle. The semicircle. That'd be part C. Okay, is there anything that we did in part A or B that we have to use for C? Yeah, there is. So let's look at this first. don't even think I need all that. All right, let's see what the directions say. So we get all this on here. It says find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4, with the indicated cross sections taken perpendicular to the x-axis. So we've got this as our base. We've got a coordinate plane. If you've got x squared plus y squared equals 4, that's a radius of 2, and the center's at the origin. So there's a perfect circle with a radius of 2. Okay? So then out of that grows these different looking cross sections. Okay? On one of them it's squares, on one of them it's equilateral triangles, on one of them it's isosceles, on this one it's semicircles. So on your paper, have that graph either actually or visualize it, and then from that you've got to visualize little semicircles popping up off of your paper to make it a three-dimensional object. The semicircles that are here are going to be smaller than the semicircles across there, right? Because they got a smaller diameter. So the smaller the diameter, the smaller the semicircle. So it gets you a dome effect. It's going to look like a dome when it's all filled in. Make sense? Okay. Now, if x squared plus y squared equals 4 is our function, let's go ahead and solve that for y. So I subtracted x squared. I took the square root of both sides. Turns out it's not really one function. It's 2. Okay? Now, and I think I can go to here now. So now, that means if this is our graph, there's the x-axis, there's the y-axis, that was the circle, that's the base, okay? So, won't the radius be the distance from, well, let's just look at the one that's the biggest circle. That's the easiest one to visualize. All I need is a representative circle, right? And you can sort of see where they had semicircle, I mean, where they've drawn one in there. So there's that semicircle. So those two little red semicircles are the same one. Okay? So to work with the area of a cross section, because remember how, well, there it is. Remember what our little formula is. It's the area of a cross section times the thickness of it, and then we're going to take the integral of it so that we accumulate all these little cross sections. But the area times the thickness is what gives it a volume. All right? The thickness is dx, and so we need the area of it. Well, look, we know good and well that the area of a circle is pi r squared, so that the area of a semicircle is half pi r squared. So we need to know the radius. Okay? Well, if that's bounded by two functions, one being the square root of 4 minus x squared, and the other being negative square root of 4 minus x squared, if you put those two together, and I still think it's probably easier to look at it as if you were above it looking down, okay? So you've got a little semicircle right there. I know my drawing sucks, I know that. But can you see what I'm doing? That little dotted one's supposed to be sticking out of the screen at you, okay? If you've got that, so the radius, well, let's put it this way. The distance from here to here, that distance is one function. The other distance, that x-coordinate, or actually y-coordinate, would be the negative of 4 square root of 4 minus x squared. But as far as a distance goes, it's square root of 4 minus x squared. So isn't the radius of that semicircle the square root of 4 minus x squared? You with me? It's actually easier if you think of it as it being the largest semicircle that you could get right there. It's more obvious maybe, okay? But that's the way it's got to work. I also thought of it this way, and this is what this is about, okay? If the semicircle connects those two graphs, well, then the distance between those two graphs, like we just got through doing, one minus the other, or the positive one minus the negative one minus a negative plus. So I get 2 times the positive one as the distance between the two graphs. Well, that would be the diameter of the semicircle. Since the semicircle stretches from one graph to the other, that's the diameter of it. And if that's the diameter of it, the radius is half of it. So 2 ways, I hope one of them makes sense, to know that the radius is the square root of 4 minus x squared. Y'all with me on that? Because if you are, we got it beat. All right. And this is awesome. You get to square the square root. Makes things a little easier. So that's what our area is. Our area is 1/2 times pi times 4 minus x squared. All right. We'd already decided that for the base, the circular base, the radius was 2, right? X squared plus y squared equals 4. So the r squared is 4, the radius is 2. So doesn't that mean that the limits of integration have to go from -2 to 2? All right, because it goes 2 in the positive direction, 2 in the negative direction. Okay? So those are the boundaries of the graph. So from -2 to 2 of 1/2 times pi times the quantity, 4 minus x squared dx. So that's the area of the semicircle. That's the thickness of the cross-section that makes it a volume instead of just an area. With me? All right. And circles are symmetrical. So I can make that 2 times the integral from 0 to 2. Makes evaluating it a little bit easier. So that's all I did there. And then something even better happens. 2 times 1/2 is 1. Set the pi out in front. And all of a sudden, this is an easy integral to evaluate. And not just easy because it doesn't have inverse trig and e's and natural logs, but I mean, that's just flat out easy. And I think you can watch it from there. Yes. All right. Let's be done with that.